We've talked about expected value of a random variable, sort of the best single number that describes all the possibilities for that random variable. Now we're also going to need to discuss expected value of functions of that random variable and expected values of sums of random variables. So recall that given a discrete random variable, x, we write little p of little x for probability that our random variable capital X takes the value little x. And we define expected value of x to be the sum over all values little x of the random variable capital X, x times probability of seeing that value. So this is a weighted average of all possible values of capital X. And we need capital X to be a discrete random variable. Discrete meaning it takes only finitely many different values, or possibly countably infinitely many values. So it has to be discrete because otherwise we wouldn't be able to compute this sum. We can't sum over an uncountable set like all the real numbers. If we had a random variable that took on all possible real values, that sum would have to turn into an integral. And in fact, it will later in the course, but we'll postpone that until later in the course. Now, if g is any function of a single variable, then we could plug in a random variable for that variable. To get a new random variable, g of capital X. So this random variable g of capital X takes value g of little x whenever capital X takes the value little x. So that gives us a sort of obvious definition for expected value of this new random variable g of x. We define the expected value of g of x to be the sum of g of x p of x over all values x of capital X. And this is a weighted average. So weighted average because of the probabilities of all possible values of g of x. And possible values are right there. So for example, let's roll a 6-sided die. And if we roll, let's say K, then color in a K by K grid. And let's compute what is the expected area colored in. And the answer is it's 1 squared with probability 1/6. It's 2 squared with probability 1/6. 3 squared with probability 1/6. 4 squared with probability 1/6. 5 squared with probability 1/6. And 6 squared with probability 1/6. So if we factor out the 1/6, this is 1 plus 4 plus 9 plus 16 plus 25 plus 36, which is 1 and 9 is 10, 4 and 16 is 20, so it's 30 right there. 55, 85 plus 6 is 91. 90 over 6 is 15, so this is a little bit bigger than 15. That's the expected area that we've colored in after rolling a die and then coloring in a grid whose sides are given by the roll of the die. All right, let's look at a couple of very simple functions of a random variable x. Here's two special cases. If b is a constant, then expected value of b is just b, and expected value of bx is b times expected value of x. Well, the expected value of b being b is not too surprising because this is b with probability 1. So if we sum all possible values of b, which is b, times the probability, which is 1, we get b. How about this? We take a random variable, multiply it by b, the expected value of that product is b times what we'd expect x to be. So this should be the sum over all values little x of big X, b times x, probability of x. Well, b is just a constant, so we can take it out of the sum. So it's a sum over all values little x of x, p of x, but this is just expected value of x. So expected value of a constant is that constant, and we can pull a constant out of expected values. Now more generally, if x and y are random variables, then the expected value of their sum is just the sum of their expected values. And this works, you might think, well, maybe they need to be independent for this to be true, but actually this works even if they're dependent. So let's see why. So this is the sum over all possible values x of capital X and y of capital Y. Little x plus little y is the sum, times the probability that x, capital X equals little x and capital Y equals little y. Alright, now let's use the distributive law to break up this sum and the product of this probability. So this is the sum over x and y. X times the probability that capital X equals little x, capital Y equals little y, plus the sum over all values of x and y times the probability that capital X equals little x, capital Y equals little y. Now we can rewrite this product as probability that capital X equals little x times the probability that capital Y equals little y, given that capital X equals little x. And let me leave that other sum alone for now. We can just work on the first sum. Alright, this little x and probability that capital X equals little x can come outside of the y sum because there's no y's in there. So these are just constants as far as sums over y go. Alright, now I claim that this inside sum is just 1. Because if we're summing over all possible values of y, then the statement capital Y equals little y defines an event, and all of these equalities, capital Y equals possible values of little y, are mutually exclusive and exhaustive. We're summing over all possible values that the variable could take, and it couldn't be two of those values at the same time. So if we have this circle being the event that capital X equals little x, then the events of capital Y being, let's say, y1, capital Y being y2, capital Y being y3, etc., fill up the whole area that represents capital X equals little x. So if we take the probabilities, this pi slice over the whole region, this pi slice over the whole region, they're going to add up to 1. So this is just 1. So that means that this first sum just turns into sum over values little x times probability that capital X equals little x. And that's just expected value of x. Similarly, now if we look at the second sum, the same thing's going to happen except the roles of x and y are reversed. So this is just expected value of y. So our claim, which I've erased, which was that expected value of x plus y equals expected value of x plus expected value of y. Well, we can see here, because we got expected value of x plus expected value of y. So let me rewrite that. In fact, expected value of x plus y equals expected value of x plus expected value of y. Also, we could say expected value of constant times x plus some other constant times y equals a expected value of x plus b expected value of y, because constants come out of the expected value. And if we can break up a sum, then we reduce to the special fact that I put up before. And also you could write a sum of three random variables as a sum of two and a single random variable, and proceed by induction. So if we have some linear combination of random variables, say ai times the variable xi, then that turns out to be a sum of ai times expected value of the ith random variable. So in other words, I guess I could sum this up by saying the sentence expected value is a linear function of random variables. So it respects sums and it respects scalar multiples. So let's do one example that uses that fact. So let's do two experiments. Let's roll a six-sided die and choose a card from a standard deck of cards. And let's say we get K dollars for choosing a card with value K, and I'm going to let Jack be 11, Queen be 12, and King be 13. And actually, let's get $2K for choosing the card with value K. And let's say we lose $1, lose C dollars for rolling C on the die. So the question is, what's your expected prize if you play this game? Alright, so we're going to use this rule. We just need to define x and y. Let's let x be the number rolled on the die, and let's let y be the value of the card chosen. Then we want the expected value of negative the number rolled on the die, and 2 times the value of the card. So this is just minus expected value of x plus 2 expected value of y, because expected value is linear. Expected value of x is, so we've got the numbers 1, 2, 3, 4, 5, 6, each occurring with probability 6. One and 6 is 7, 2 and 5 is 7, 3 and 4 is 7. So we've got 3 sevens are 21 over 6, divided by 3, 7 halves. Expected value of y is, we've got 13 cards numbered 1 through 13. Of course, there's 4 of each in the deck of 52, but each of the values has probability 4 over 52, which is 1/13 of being chosen. 1 plus 2 plus 3 up to 13. Let's see if we can add that in our heads. I think we can. If I write it out like this. So 1 and 13 is 14. 2 and 12 is 14. 3 and 11 is 14. So I'm going to write 1 plus 13, 2 plus 12, 3 plus 11, and then 6 plus 8 is 14, and then there's going to be the 7 that doesn't pair with something bigger, plus 7. So it's 1/13 of 14 plus 14 plus 14, 6 14s, plus 7. Let's factor out a 7. Equals 7/13. 6 times 2 plus 1, which is, well, that's convenient, that's 13. 7 times 13 over 13 is 7. Okay, so the expected value of y is 7. We want expected value of negative x, or sorry, minus expected value of x plus 2 expected value of y. So that means that minus expected value of x plus 2 expected value of y is minus 7 halves plus 2 times 7. So 14 minus 3.5 is 10.5. So that's the amount of money we expect to win by playing this game. The end.